GD&T done right. Simultaneous requirements. Presented by Gavril Tartalev, COTEM, Division of Quality Vision International. First, let us try to answer the question, what is simultaneity? The rule of simultaneous requirements applies to all position and profile tolerances referring to a common datum reference frame. For example, here we see several features whose feature control frames reference the same datums in the same order with the same modifiers. These features are considered as a composite pattern, whose tolerances must be met at the same time. Here are the requirements for simultaneity. First, all features must reference the same datum reference frame. Second, the datum reference frame must have mobility. Mobility can be achieved when the datum reference frame is not fully constrained or when the datums are referenced at maximum material boundary or least material boundary. Third, simultaneity applies only to tolerances of profile or tolerances of position. Simultaneity does not apply in the following two cases. The first case refers to the lower segments of feature control frames. If we have several FCFs with identical tolerance types, datums, and datum modifiers, then simultaneity applies only to the uppermost segment, which can control location and orientation. The lower segments of a feature control frame control orientation only, and simultaneity does not apply to them by default. Secondly, simultaneity does not apply to form and orientation tolerances. In the example shown here, simultaneity does not apply to the orientation and profile callouts, even though datum A is referenced in both FCFs in the same manner. Let's look further into the differences between simultaneous and separate requirements by comparing the two tolerances in this example. On the left, we see that simultaneity applies to the four feature control frames because datums A and B are referenced in the same order with the same modifiers. These four feature control frames are equivalent to a single feature control frame, tolerancing the four holes as a pattern, which can also be seen on the left. On the right, we have the same four feature control frames appear with the notation separate requirements included with the FCF. This notation overrides the simultaneity set as default by the ASME standard. Datum B is simulated at the maximum material boundary as shown by the M modifier. This part could be inspected by a hard gauge where the datum is simulated at the virtual condition. This gives mobility to the feature control frame. Let us represent the gauge and the measured points as shown on the right. For simplicity, we will consider this as a two-dimensional problem. The datum is represented by the large black circle in the center, and the four tolerance zones are the smaller black circles with crosshairs. The measured datum feature is represented by the red circle, and the axes of the four measured holes are represented by the four red dots located near the outlying holes. In a 3D reality, these axes could be tilted with respect to datum A. The requirements on the drawing ask us to find the location of the part with respect to the gauge, in which the deviations of the four cylinders with respect to the nominal is the smallest. In our two-dimensional problem, this means that the part is allowed to translate in X and Y and rotate in the XY plane in order to minimize the largest deviation of any of the holes. Let us observe what that means in our case. As the gauge moves with respect to the part, the black circle representing the datum must not penetrate the datum feature. However, the gauge is free to move in X and Y and rotate in the XY plane in order to bring the red points as close to the crosshairs as possible. Now, let us consider the separate requirements case. The model is the same except for the notation separate requirements above the feature control frame. This time, the different points are colored differently to remind us that they need to fulfill the FCF requirements separately. Since the datum reference frame has no alignment constraint, each of the axis tolerance zones is allowed to translate and to rotate around datum B in order to minimize the deviations of any of the axes. When the datum feature simulator touches datum feature B, we can see the closest and the farthest away the gauge can get from the part. This determines the boundaries of the tolerance zones. Let us now consider what that means for each of the feature control reference frames. In order to get the axis as close to the crosshair of the top left tolerance zone as possible, we can translate in the XY plane. You can notice that when that happens, all other points are outside of their tolerance zone, but that does not really affect the top left hole results. Similarly, we can just translate the top right tolerance zone as much as we can in X and in Y in order to bring the axis as close as possible to nominal. Again, all other axes are out of tolerance. To take care of the bottom right point, we could rotate the gauge and then translate it in X and Y. This would bring the point as close to nominal as possible. Similarly, the last axis point could be brought as close to nominal as possible by a rotation and a translation. Here we can numerically compare the differences between enforcing and releasing simultaneity of the four-hole pattern. Releasing simultaneity allows more freedom in the positions of the four holes with respect to the datum, which leads to smaller deviations. Enforcing simultaneity maintains the mutual relationship of all points to the tolerance zones, which may be crucial for the part to fit in the assembly. Which specification is best depends on the functional requirements of the part. Let's look at one final example to illustrate the difference between simultaneous and separate requirements. Here we see a part with profile tolerances applied to several features. Again, the deviations of the 0.35 profile to A are larger when evaluated simultaneously than when evaluated separately. In summary, simultaneity ensures that features in the same datum reference frame are treated as a pattern. Separate requirements can be specified to override the default behavior in the ASME standard. The correct specification of simultaneous or separate requirements depends on the design intent for the part. To comply with the designer's intent, the GD&T evaluation software must be capable of evaluating simultaneous or separate requirements.